We are the leaders of Lidar, and this is our project.
Made to wave the flag, ooh, they're red, white, and blue. And when the band
Lidar is used extensively in forestry to help map terrains and forest canopies. Implementing Lidar provides advantages over radar and other traditional methodologies. Estimates of the vertical structure of the vegetation can be made directly from Lidar, while radar and other methods are not as sensitive to these vertical measurements. The project sets out to develop a system in which a Lidar is used to map the canopies of trees.
The device and system developed is known as the Tree Mapper. The purpose of this device is to be able to map the canopies of individual deciduous trees as a proof of concept project. The device is a battery-powered Arduino-driven device attached to a drone. The imaging software is a MATLAB program that plots and interpolates the data collected by the Lidar.
The device collects spherical coordinates and outputs them to a text file. The stepper motor gives the theta angle, and based on a certain number of steps taken, tells the Lidar to take a measurement. The microserver gives the phi angle in increments after a full rotation of the stepper motor. The Lidar itself is only taking the distance measurement, which acts as the radius and spherical coordinates. The test data is written onto an SD card so that the data can be processed on a computer.
The DJI Mavic Pro was chosen for the project because it has 27 minutes flight time with full battery, a 7 km control range, and 5 km max flight height. The most important feature of the Mavic Pro is that it can take off with a 900 grams maximum payload. Once the drone was chosen, the attachment for the device was designed. A lower mount bracket was found that attached to the Mavic Pro without any difficulties. It has a triangle hook which contains 3 damping balls that can reduce the vibration. The contact point with the Mavic Pro can be easily stuck in. Metal brackets and the motor shaft hub connect the Lidar motor bracket and the stepper motor to each other. The stepper motor was attached to a bracket connected to the triangle hook. The stepper motor shaft was connected to the tilt bracket, which held the stepper motor and the Lidar. Finally, Velcro was used to attach the Arduino and the battery to the drone.
A stepper motor and a servo motor were used to move the Lidar in the conical shape. The stepper motor rotated the Lidar 360 degrees in one direction, then the servo motor tilted the Lidar upward by 2 degrees. Once this was complete, the stepper motor would rotate 360 degrees in the opposite direction, and the servo would tilt the Lidar up another 2 degrees. This process was repeated until the servo motor was at 60 degrees.
The Arduino is responsible for controlling the movement of the Lidar as well as taking and recording distance measurements. The stepper motor and servo utilize libraries that allowed for straightforward control. The Lidar is accessed via I2C, and custom software from Garmin was used to capture the distance measurements. At each increment of the stepper, a measurement was taken and stored in a text file using spherical coordinates to correlate the distance measurement to the position of the stepper motor and servo. These coordinates were stored on an SD card for easy transfer to the interpolation software.
The MATLAB program takes in spherical coordinates and then converts them to Cartesian coordinates. The program then uses the MATLAB computer imaging suite to place the points on a 3D grid and create an interactive 3D image. It creates a 3D plot of the raw data and then interpolated graphs using linear, cubic, natural neighbor, and nearest neighbor interpolation methods. The TeamLOL MATLAB program provides results with similar accuracy as ArcGIS. Shown here on the top left and bottom left are the point clouds generated by MATLAB and ArcGIS respectively. Displayed on the right side are the 2 most common types of interpolation we use, which are the cubic and natural neighbor interpolation methods.
A lot of problems that we faced were with the hardware. The first challenge that we faced was with the stepper motor. Essentially, its library was supposed to allow for speed control and to set the number of steps based on the number of steps for the given stepper motor. So I should have been able to tell it to take 64 steps and then it should have gone a full rotation. I also should have been able to vary the revolutions per minute between 10 and 20, but this also did not work. The solution we ended up going with was to do trial and error measurements to determine the number of steps the stepper motor needed to take to perform a complete rotation, which turned out to be an arbitrary value, 815.
Another issue we had was with the motor bracket. It didn't come with setup instructions, and we ended up putting it together incorrectly at the first time. Hardware and hobby kits seem super easy, but small challenges can cause big problems when there is a deadline around the corner that you are rushing to make.
The biggest and most consistent challenge that we faced was the wires getting tangled, which caused the device to stop turning. The solution that we came up with was to fix the wires to a certain length on the part that rotated. They are fixed just below the stepper motor, which allowed us to change the length of the wires traveling to the Arduino so that they can be extended or shortened with ease. With this fix, the device is now able to rotate 360 degrees forward and backwards.
The device's accuracy was confirmed by testing it in a number of enclosed spaces. First, when the design wasn't yet battery-powered, the power supply was moved to an empty corner of the senior design lab and it was set to run a full device scan. Unfortunately, the corrugated ceilings and the high amount of reflective surfaces caused the scan to be very inaccurate. The experiment was revised so that the LiDAR would instead travel only 90 degrees with the stepper, so the empty corner of the lab could be captured. The LiDAR measurement mode was selected based off which setting provided the most accurate rendition of the wall and corner.
Check it out, Team LOL in action. It's Caleb and Joe working on their thingamabobber. There's Alex. Ooh, look at all that cool stuff. There's Thomas, the bright, shining joy of our group. And this is our project right now. The next set of tests we did were once we had gotten the device to be battery powered and attached to the drone. This was really important because it allowed us to get out of the lab and to do testing. The first test we did was under this gazebo at Watson Park, and the results are shown. The green area is the edge of the roof that you see in the photos. This showed that the LiDAR does work on the ground, on wood, in stable environments.
In total, we did 3 sessions of outdoor testing. The results from the first round of testing were a mixed bag. We had good data from underneath the gazebo, but bad data from an aerial drone test above a tree. The second day of testing was a total bust due to the high wind, and this helped us realize one of the limitations of our project, which was that the device really only operates well in low wind conditions.
The aerial testing was rough at first. We couldn't get the drone to fly the first time we went to test because the sensors were blocked by the device. The next time, the wind was too severe, but the third time testing, we were able to capture good results with the DJI Mavic Pro's Intelligent Flight Mode feature, Tripod Mode. The first day of testing was still exciting because it was cool to see the drone flying with our device attached to it.
Once we got it in the air, it really wasn't that bad, but we had a lot of issues getting it off the ground. Whether it was a loose wire or a dead battery, often we thought we'd be ready to go once we got to testing, but then something would break and we would spend half an hour fixing it.
Watching the device work on the drone was very cool, but it was also very nerve-wracking having to watch Zhao land it in his hand, especially when the battery on the drone got low.
In general, as a pilot of the drone, I have to say that the Mavic Pro is very easy to control when you are flying it. Even when it has 400 grams payload on it, piloting the drone in the tripod mode made it much easier to control and allowed the sensitive LiDAR to get good data.
The results provided insight into the function of the device. For the gazebo, it successfully identified the outer edge off the roof. For the test between the trees, it was able to identify the canopy directly above it and the stumps of the 2 trees, but not their overall shape. The second round of testing was unsuccessful because of high wind. This illustrates the importance of the device remaining nearly perfectly still.
The third day of testing brought on changes in the Arduino code. The code was altered to cut the stepper interval rotation in half between measurements, effectively doubling the number of data points captured without increasing the runtime of the device. This was critical to the success of aerial results. By increasing the number of points, the interpolation of the data was much clearer despite the increase in erroneous measurements as well.
The third day of testing was very exciting because when we put the drone up in the air, the tripod mode worked without the altimeter on, which was one of the sensors we disabled, so we knew we had a chance to collect good data. The tripod mode limits the speed of the drone to 2.2 miles per hour and limits the controller's movements. Although this did not provide perfect stability, the vibration dampening balls were enough to keep a lot of the drone vibration from reaching the stepper motor. The drone was also able to stay at about the same height and position, so unlike the past couple of times, and with the LiDAR capturing twice as much data, enough was gathered.
When we were inspecting the data in film, we realized that any good measurements would be over 1 meter away based on where the drone was above the tree. The LiDAR measures the distance in centimeters, so any data point under 100 should be eliminated. Unfortunately, this meant that the LiDAR took a lot of bad data, and if no knowledge of the area under observation were known, then it would be difficult to reconstruct the image.
I think the results show that the system could work in the real world, but design changes would need to be made in order to improve the device's stability and accuracy. This is the first prototype of the device, so a lot of mistakes were made. I think some improvements that could be made to version 2 of the device would be to use the drone-specific microcontroller. This allows for lots of exciting possibilities. Like the data could be stored on the drone's onboard microSD card. The drone can be programmed to fly in a circle, and with the microcontroller, this position can be mapped precisely, which can be used to trigger the LiDAR to take measurements. The need for the theta, or full rotation motor, is eliminated. All you need is the angle phi changing microservo. This would drastically decrease the size, weight, and power consumption of the device. The need to use the Arduino was because the LiDAR had a library for that microcontroller, which made programming it feasible. But with our improved programming skills from this project, version 2 would be possible. Say hi, everybody.